Get started. Everybody. Thanks. Okay, guys. Are we all good? Great. So I hope the midterm was good. I hope it went well. I expect it went well in general because I think the questions were not so hard, and then I think we've seen many of this type. So yeah. And someone told me that the hardest question was at the very first question. So, and I totally apologize for this. This was not, if that was the case, this was not, made on purpose. So, but I think it's, I didn't think of it really. So what I had in mind when I was writing this, I had this in mind, and then I remembered that I had put this on the quiz, right? So I said, okay, let's put it here. This was it, that was the logic behind it. It's not so that I wanted to trick you or something. But in general, besides this question, everything else was good. Great. Okay, so let's continue where we left off last time. We're doing an example. Find and classify the local minimum and maximum and saddle points of fxy. What did I pick last time? It's x minus y. Y minus xy. So what is that? We expanded that. I don't know if you have to expand it, but guys, so this is just x minus x squared y minus x squared y minus y plus y squared x. Then what is fx? xy. This is 1 minus 2xy, right? Minus 2xy plus y squared, is that right? Is that right? Yeah, is that right? Looks good to me. X minus x squared y minus y plus y squared x. And what is that yxy? What is that? This is minus x squared minus 1 minus x squared minus 1 plus 2yx. Now solving these two is equal to 0, right? So fyxy equals 0. What do we get? We get y squared, we get 1 minus 2x, or we can subtract both or add them here. Just let me be sure that is that the example I had last time, or I had y minus x? I had this one. Can you double check? I had this one. Okay. So let's add them both. So what do I get? This is equivalent to 1 minus 2xy plus y squared is equal to 0. And let me add them both. What do I get? I get y squared minus x squared is equal to 0. Is that right? Yes? Do we see that? Let me add them both. Is that good or not? Yeah? So how do we solve this? So this is y is equal x, or y is equal minus x. Let's plug that back in. If y is equal to x, what do I get? I get 1 minus 2x squared plus x squared is equal to 0. So I get that 1 minus x squared is equal to 1. So x is equal to 1, or x is equal to minus 1. So what are my points? If x is equal to 1, then y is equal to 1. And if x is equal to minus 1, then y is equal to minus 1. Right? We see that? Everybody? Great. Now, if y is equal to minus x, what do I have? I have 1 plus 2x squared plus x squared. So I get 1 is equal to 0. So 1 plus 3x squared is equal to 0. So I have no solution. Okay? Is that clear? Is that clear, everybody? Yes or no? Now, what? So let me compute fxx. What is fxx, xy? So those are my critical numbers. Fxx is what? Let's differentiate with respect to x. So what do I get? Minus 2y. What is fxy? I mean, what do I have here? Fxy or fx? Or fyx? I think I have fxy. I mean, it doesn't matter in that case, but usually I forgot the Hessian in most of the cases is symmetric. So let me just sorry. Oops. Fxy. So I have fxy. What is fxy? Differentiate fx with respect to y. What do you get? You get minus 2x plus 2y. Is that right? Everybody, is that right? Yeah. Differentiate fy with respect to x. What do you get? What do you get? You get minus 2x plus 2y. Is that a good sign or not? Yes, a good sign that my partial derivatives are equal. And let's look at fyy. So what do we get as fyy? It's 2x, right? Okay, so these are my critical points. So I compute, I look at the point, so I have the point AB, then I have fxx AB, and then I have D, and then I classify. So if AB is 1, 1, what is fxx AB? It is minus 2, right? Everybody? Are we good? And what is D in that case? What is D in that case? What is D in that case? It's minus 2 here and 2. Minus 2 plus 2, what do you get? 0. So you get minus 2 times 2. What is that? Minus 4. What is the sign of D in that case? Do you know where this result comes from? The D positive and fxx positive, or fxx negative and D positive. Do you know where it comes from? I don't know if the book has it, but really it comes of positive definiteness. Do you know positive definiteness? Have you seen that? Symmetric. So this is a symmetric matrix, right? You agree that the matrix here is symmetric. What can you do with a symmetric matrix? 1, 2, 3. What can you do with a symmetric matrix? Not necessarily. If the determinant is 0, you may not be able to. What can you do with a symmetric matrix? You can? Transpose. Sure. Transpose it is equal to itself. Something else? Diagonalize it, right? Did you see that? Didn't diagonalize the matrix? No? Yeah. So really, this tells you when the eigenvalues are both positive and when the eigenvalues are both negative, and when you have a 0 eigenvalue and things like that. Okay? These are the cases that break. The cases here that, you know. Anyways, so what is D in that case? Did I mess it up or no? I think that's good, right? So what is D? D is a saddle. When D is positive, What is the determinant of a diagonalizable matrix? It's the product of the eigenvalues, right? You know this? Yeah? Have you seen that? So if D is positive, this means that both eigenvalues have the same sign. Okay? So they're either both negative or either both positive. And what will help determining these is just fx, the sign of fxx, if D is positive. Now if D is negative, what can you say about these two eigenvalues? It means they have opposite signs, okay? And it's the same for -1, -1, right? So -1, -1, what's fxx? It's 2, blah, 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 right? You see that? So fxx is, doesn't matter, I mean, it's 2, and D is still -4, that. Okay? Should we do one more, or that's good? Let's try something one more. Let's try to do one more. Let's see. Should we do one more? That's not. We do one more, or that's good. Yes. One more. Let's do one more. X cubed minus 3x. Okay, then we move on. X cubed minus 3x plus 3x plus squared. Okay, so let's differentiate with respect to x. What do I get? So I get 3x squared minus 3 plus 3y squared. Oh, sorry, fx. And let's start to differentiate with respect to y. What do I get? A differentiate with respect to y, what do I get? I get 6xy. Right? Everybody? Right? I want to solve both of these is equal to 0. So I get 3x squared plus 3y squared is equal to 3. So x squared plus y squared is equal to 1. And 6xy is equal to 0. So let's derive this. Okay? Now, if x is equal to 0, what are the values of 1? What are the values of y? Say x is equal to 0, y squared is equal to 1. So what are my critical numbers? 0, 1, 0, minus 1. That's one thing, right? Zero, 1, 0, minus 1. Now if y is equal to 0, what are my critical points of an x? So it's 1, 0, minus 1, 0. Are you clear or not? Can you sketch these two? Like you can sketch it like that. This is the square, the circle, and then you find the points where one of the coordinates is 0. So you have these points. Great, awesome. Now let's classify them. Let me look at the derivative here. Let me look at the fxx. What's fxx? It's 6x, right? 6x. fyy, what is fyy? It's also 6x. Is that it? Yeah, so 6. So yeah. 6x. That's weird, okay. What is fxy? Fxy is equal to what? Differentiate 6, well let's do it properly. It's 6y. And what is fyx? I mean, sure. Fyx is what? It's also 6y, right? So what is the discriminant? What is the determinant here? dxy is equal to what? is just 36 x squared minus y squared, right? We see that? That's easy to compute, okay? Usually you can plug in the numbers, it makes it easier, but here it's not bad to compute. It's 36 x squared minus y squared. So let us look at the critical points. So AB, fxx, AB, D, and classify. What is AB? So let's start with 0, 1. What is fxx AB? Is equal to 0. And D is, what is D? Is minus 36, right? Which is negative. So what do I have here? Okay, now I start 0 minus 1. Also 0. It's minus 36. I also have a side. Now what do I have? I have 1, 0. What is fxx? This is 6, which is positive. What is discriminant? 36, which is positive. So what do I have? Local. What do I have? Local? Minimum, right? Local min. So f11 is a local min. Sorry, I have minus 1, 0. So what is fxx? It's minus 6, which is negative. So this determinant is still 36. So I have a local. Okay. It's good. It's good. Yeah, okay. Great. Okay, I mean, what is the value of the local domain? It's f10. What's f10? So it's 1 minus 3. So it's 1 minus 3, which is 1 minus 3, which is minus 2. And what's f minus 10? It's minus 1 plus 3, right? Minus 1 plus 3, which is... Okay, great, fine. Now, let's go back to something else. If we have seen in calculus 1, and we will generalize it in calculus 3. Absolute max. And then over closed bounded. So in calculus 1, if I give you a continuous function of AB, if f is continuous on AB, what do I know about f? We know that f has a maximum and f has a minimum at this interval, right? You remember this? Remember? So f has an absolute max and absolute min on AB. What were the steps that we took to find this absolute max and this absolute min? First, we found the critical points, right? You remember this? We computed the value of f at those critical points, right? And then what did we look at? The boundary points, right? The smallest is the absolute min, the largest is the absolute max. Remember this or no? So find the critical points. Critical numbers, basically. So we assumed, I mean, it was an assumption that f is differentiable, so not every time though. calculus 1 a little bit. Yeah, so it's not everywhere, but I mean, you know, function where it's not differentiable, or where the derivative exists and is equal to 0, right? And compute the values of f at each of those points, of those numbers. And then of course your AD are numbers, right? They're not infinite. AD are real numbers. And then compute f A f b. Compute f A f b. The largest value of steps 1 and 2 is the absolute max of f on AB, and the smallest is the absolute range. Right? You remember this? Yeah, you remember this thing that we have seen in calculus 1? Okay, great. Now we're going to do the same thing in calculus 3. Well, not the same thing, but we're going to do it in 2D now, in x and y. I don't think we're going to do, well. Now in calculus 3, now, here I want you to rely more on your intuition. Definitely, I will not define things very properly. This is not an analysis course. So, we will not define things properly, but I want you to rely on your intuition. Okay? If I give you the xy axis, okay? And let's draw this line here. And let's draw those two parallel lines, okay? Those are two parallel lines. And I tell you, consider the region between those two lines, between those two parallel lines. Is this a bounded region? Is this a bounded region? Your intuition, what does your intuition tell you? Is this a bounded region?
No.
Yeah. It is?
It's not.
It's not. Why it's not?
Because it has no, it goes on the limit.
Exactly. So it goes on it goes, you know, it never stops. Now if I tell you, let's draw this one. Inside this circle, inside the disk, is it a bounded region? It's bounded. Okay, very good. Unbounded. Let's draw one more. Bounded or unbounded, the one inside? What do you think? Bounded, right? You see? Is that intuitive for you? Yeah, if I give you a region, can you tell me if it's bounded or not? Okay. Basically, a bounded region is a region that you can contain in a disk around the origin. Let's take this definition. Okay? In R squared, say, is a region that you can contain in a disk around R squared. Okay? Yes, sir.
Which would be just be another bounded region.
Pardon me?
Which would be another bounded region.
Do you want to draw another one?
No, I'm saying that your definition is just a bounded region, anything that can be contained by another bounded region.
Exactly. The disk is, of course, bounded, right? What is the distance from a point on the disk to the origin? R, exactly, the radius. Now, what is the distance between two points? What is the largest distance between 2 points here? Diameter, right? a bounded region. Definitely, we won't go into details what bounded means, but for now, this is just for you to think that this is bounded, this is unbounded. Is this class bounded? Is it an unbounded region? Yeah. Okay. Awesome. Now, let's look at. So we have a closed and bounded interval. We saw what an analog of bounded is. Now we have to see an analog of closed. So this is bounded and bounded in 2D. Now what else do we have? An analog of closed, right? How to check if a region is closed? Let's take the test such that x squared plus y squared is strictly less than 1. That's a disk. Now, does this disk have a boundary? What is the boundary of the disk? The circle, right? Now, is this region that I drew, is it closed or not? I don't think they do it physiologically. Is this a closed region or not? Is this closed? Does it look closed? So, let's think in terms of interval. Is this interval closed? Why is it not closed? Why is it not closed? You called it not closed, right? But why is it not closed? The left endpoint is not included in the interval. Now, in this interval, can you get as close as you wish to 0? If I tell you I want to be 1 over 10 million close to 0, while staying in this interval, can you get there? Yeah. If I tell you I want to be 1 over 72 billion close to 0, can you get there? Now, can you get 0 close to 0? No, because 0 is not contained. Now, if I tell you on this set, work on, let's work with this. I have the rectangle here, right? This is a rectangle. Well, this is the inside of a rectangle. And this is my boundary. We agree? Suppose that, I consider the region without these boundaries. Everybody, can we see here? Can you see here? Now, so I'm not allowed to cross the boundary. Say there's a border, for example. You're not allowed to cross the border. I mean, let's do it here. This is the border, say. What is better, on the table or here? Table is better. So this is the border that you're not allowed to cross. Can you get as close as you want to the border? You can get as close as you want. But are you allowed to cross?
No.
Now, if this border is not on your set, can you say that your set is closed? By the same analogy here. Can you say that if the border is not in your set, can you say that the set is closed? No. Okay? So the idea is a closed set is a set that contains its boundary points. Boundary points, let's not define this. And anyway, let's not worry about this. Okay? Now, what are, I don't know how this book is defined. Yeah, okay, so just say, it says it contains all its boundary points, so they don't define what boundary point is. But technically, what is the, intuitively, what is the boundary point of this disk? What is the boundary of this disk? Yeah? R equals 1. So this is, you're in a disk, you're the disk, and you're just not allowed to cross the circle. What is the boundary of this disk? It's the circle of radius 1, right? This is the boundary. How can you characterize it? X squared plus y squared is equal to 1, or r is equal to 1, right? Now if I include my test here, and I include the circle. So really my test is that x squared plus y squared that's equal to 1. Is it a closed set or not? Is it closed? Yes. Does it contain its boundary? Yes. It's closed. Very good. Now, okay, of course this is boundary points, it's not very clear with these, but take it intuitively. Okay, all the examples that we'll be doing are intuitive. Now is the circle closed? It's closed. Is it bounded? Is this circle bounded? Yes. Yes, this is closed and bounded. We have a name for closed and bounded sets in R squared, but we will not use them. We will not use them, sorry. Now let's draw something. Let's just sketch a region. So I draw inside of my rectangle, but I don't include this line. Is it closed? Is it closed? Everybody, is it closed? No, right? Does it contain all of my boundary? No, this one is not complete. Not closed. Is it bounded? Not closed, but bounded. Now if I draw this, so let's give it x squared plus y squared. That's really equal to 1, and y is bigger or equal to 0. Is this closed? Does it contain all my boundary? Yeah? Is it bounded? Is this circle, is this region bounded? Can you bound it? Yeah. Okay. So is it clear what a closed bounded set is? Yeah? Okay. Now, function, a continuous function. F xy defined on a closed bounded region is E R squared has absolute max and absolute min on. Okay? Now, to compute this absolute max and absolute min, how do we do? It's the same way. Find critical points of F inside D. Okay? Okay, so let's not inside D, so not on the boundary, right? Because the function technically you cannot differentiate on the boundary. Anyways, that's fine. If you get a point on the boundary, I'll just close my eyes and okay. Okay, just let's hope that you don't get anyway, inside D, critical points of F inside D, and evaluate F at each of those points. Two, find the max and min, their absolute of F on the boundary of D. And three, the largest of those values is the absolute max. And the smallest on D of F on D. And the smallest is the absolute min of F of. Okay, let's give an example. Let's see. I have a nice example here, I guess. What is my rectangle? 0, 3. Let's do it. Find the absolute max of fxy, x squared minus 2xy plus 2y on this set 0x3 and 0, 1. How do you sketch this set? What is this set? It says x is between 0 and 3 and y is between 0 and 2. How do you sketch it? Right? Is this a bounded set? Is it a closed set, everybody? Is it closed? It contains, what is the boundary? It's the rectangle. Right? So is that continuous? F is continuous. So what do I know? That F has a absolute max and an absolute min in here. Right? So first of all, what do I need to find? I need to find the critical numbers of F, the critical points of F. What do? I compute, what do I compute? The derivative, the gradient of F, right? 1, so what is the gradient of F? You know, yesterday, I'm a bit too tired. Yesterday I just didn't sleep. I was just afraid of missing the picture. I don't know why. That is weird. And then you start having dreams about it, you know, like, oh my, you missed the picture. Minus 2xy I think people also spend the night reviewing, right? A lot of you, because you're calm today. Like, there is no. Anyway, so Fy, what is Fy? Fy xy is minus 2x plus 2, right? So what is my critical number? Critical number, what is that? So f is differentiable everywhere on the inside, so I don't have to worry about points where f is not differentiable, except the boundary, okay? But let's not worry too much about that. So what is the value of x? 1, and what is the value of y? 1, right? You see that? Critical point. Everybody, do we agree with this? If I solve this 2 is equal to 0, I get x equal 1, and x is equal to y, so y equals 1. Is that clear or not? Yeah? Everybody, is that clear? Is that clear? Or do you want me to write it down? That's fine? Okay. Great. Now, what is f11? Let me compute f11. f11 is 1 minus 2 plus 2, which is 1. Okay, let's keep this in mind. And now I have to look at the boundary of f, the boundary of D, of this region. What is how many parts can I describe the boundaries? How many parts does it have? 4 parts. So let's call them 1, 2, 3, 4. And let's look at the first part. How can you characterize the first part? What is the value of y on the first part? 0. So y is equal to 0. And what is x? X varies between 0 and 3, right? Now, what is fxy on this boundary? Y is equal to 0, right? Everybody, do we agree? This is just fx0, because I'm on 1. What is fx0? fx0 is just x squared for 0, x3. Now, x squared, what is the maximum of x squared on 0, x3? At what point it happens? 3, right? You see that? Everybody. X squared on 0, x3. What is the maximum of x squared on 0, x3? It's at x equals 3 of the value of 9. Agree or not? So f30, what is it equal to? f30, what is it equal to? 9. This is the largest value on this line. Agreed? And what is the smallest value on this line? 0. Where does it happen? At x is equal to 0. Okay, so I keep those two. Let me write them down here, okay? What do I have? f30 is 9, and f0 is 0. So do you mind if I stay 30 more minutes today? 25 more minutes, yeah? Yeah? Is that fine? Okay. Because we started late. I won't start everything late, but oops, oh shoot, I wrote it. Everybody wrote this, right? No? Okay, let's do 2 now. What characterizes 2? What characterizes 2? What characterizes 2? The boundary 2 of my line. What is the value of x? X is equal to 3, and y varies between what and what? Y varies between what and what? 0 and 1, right? So what do I have? fxy is equal to f3y, right? 0 and 2. Thank you. 0 and 2. 0 and 2. Yes, thanks. f3y. What's f3y? So plug in x equals 3, so you get 9 minus 6x. No, 9, sorry, so it's 9. X is equal to 3. Minus 6y plus 2y, so it's 9 minus 4y y between 0 and 3. What is the maximum of this function and what is the minimum of this function on 0, 3? You have a function of y here, right? Everybody. So this is a decreasing function of y. 9 minus 4y. So it's 9 minus 6y plus 2y. What is the maximum? F. So when y is equal to 0, the maximum is f3 0. What is it? Is 9, right? And what is the minimum? Since it's decreasing, it says f3 3. It's 9 minus 12, which is minus 3. So f3 0, I have it already. Agree? Decreasing. 9 minus 12, what is that? Is that good? Did I? Oh. No, I think it's good, no?
Why is bounded by equation of 2?
Y is. Oh, shoot. Y is 2. Thank you very much. F3, 2, thank you. So 9 minus 4 times 2, so it's 1. And so F3, 0 is there. I have F3, 2, which is equal to 1. Okay? Are we good? Now, what else do I have to do? What part do I have to do? Everybody, what part do I have to do? Line part number 3. How can you characterize part number 3? The value is y is equal to 2, and x varies between 0 and 3. Oh, who can help me with this? So I have f11. What is f11 equal to? 1. I had f3 0, 9. And I have, oh, everything's good, alright? F3 2 is equal to what? F0 0 is equal to 0. Wait, what? I had F0 0, yeah, F0 0 is equal to 0. And F3 2 is equal to 1. Okay, great. Now I have the third part. It's y is equal to 2 and x between 0 and 3. What is that? So it's fxy, what is it equal to on this part? Just fx2. What is fx2? Who can help me? What is fxy again? It's x squared minus x squared minus 2xy plus 2y plus 2y. Yeah? So what is fx2 here? If you put in y is equal to 2, so you get x squared minus 4x plus 4, right? What is the minimum of this? What is the minimum of this function? Where does it achieve the minimum of the interval 0, x3? You want to draw it? You draw it? So you have the line, the parabola, x minus 2 squared. Right? This is the minimum. And the max is either at 0 or at 3, right? What is f of 0? 4. Right? And what is f of 3? If you plug in x equals 3. So what is the max here? So I mean, you can compute them all actually. So look at the minimum of the interval is f22 equals to 0. And then you have f32, which is 1. And then what do you have? Oh man, f3, and then you have f02, which is 4. Okay, I mean, we have f32, so f02, 4. So what line do we have left? We have the fourth line. How can you characterize the fourth line? What is the value of x? X is equal to 0, and y is between 0 and 2. fxy here, what is it equal to? It's x squared minus 2xy plus 2y. What is that equal to? It's 2y, right? it's at 0, 0. Agree or not? So when y is equal to 0. And what is the maximum? It's when y is equal to 2. So it's f02, which is 4. I have them already. I have all my points already. Do you agree? Now what is the absolute maximum of f? f30, which is equal to 9. And what is the absolute minimum? Okay? Is that clear? We do one more example? Yes?
F22 also gives 0, does that mean there are 2?
Sure. Yeah, I didn't write it. I should have written it here. F22 is 0. Thank you. Well, it means that the maximum is achieved, the minimum is achieved at 2 places, right?
So you could choose any one of them?
Yeah. What is the absolute minimum? 0. At what point? You can say at 0, 0 and at 2, 2. Okay? Great. Let's do one more. We do one more? Let's do one more. This one is a bit more complicated. Fine. Yeah, okay. Find the absolute mass. Let's see what I have. X plus y minus xy. On D, where D is a closed triangular region with vertices 0, 0, 0, 2, and 4, 0. So let's draw this. This is 0, 0, and this is 4, 0, and this is 0, 2. And I want it over this closed triangular region. Okay? So let's do that. First, what do? We find the critical points inside the region. So what is fx? What is the derivative with respect to x? What is that? This is 1 minus y, right? And what is fy? Fy is equal to what? 2. What is fy, everybody? 1 minus x, right? We see that? Fy 1 minus x. Everybody, do we see this? Yes or no?
Yeah.
What is the critical point? Critical point is is 1, 1. Does 1, 1 lie inside my region or not? Okay? Lies inside my region. So far so good. Yeah? What is F11? F11 is 1. Now the boundary, in how many parts can I decompose the boundary? 3. What is the first one? Let's go 1, 2, and 3. So the first one, how can I decompose it? How can I characterize it? Y is equal to 0 and x between 0 and 4. So y is equal to 0. So fx 0, what is that equal to? It's x, right? What is the maximum and what is the minimum of x? 4 is the, at x is equal to 4. So I have f of 4 is 0. equal to 4. And I have f of 0, 0 is equal to 0. Let me write that down here. Right? This is the max of f on this line. This is the max of f, the min of f on this line. Great. Now what do I have? I have line number 2. How do I characterize line number 2? How do I characterize line number 2? Yes. You want to say line number 3? What's line number 2? What? Sure. Y is 2 and x is 4. But y is 2 here and x is 4 here. Where are we walking? That's good. So where are we walking? I'm walking on what? On a line. How can I characterize a line? I can characterize it as y is equal to mx plus b or ax plus b, right? Or you can do it x is equal to ay plus b, whichever you want in that case. Which one do you prefer? Y is equal to ax plus b? Okay, so line number 2, how can I characterize it? Y is equal to what? So it's delta y over delta x. What's delta y? Y is 0 and 2, so it's minus 2, right? Minus 2 over 4 x. What is the intercept? 2, right? So it's minus 1 half x plus 2. X varies from where to where? 0 to 4. Very good. So what is fxy in this case? Right, so here if you had taken x in terms of y would have been a bit easier. You would have had it. Not a big deal, but what is fxy? This is just x minus 1 half x plus 2. Do you agree with that? So what is that? So I have x plus y minus xy, right? This is what I have, right? What is x plus y? This is just x minus 1 half x plus 2 minus x times minus 1 half x plus 2. So what do you get here? You get 1 half x plus 2 plus 1 half x squared minus 2x. We agree or not? Did I mess this up? Did I mess it up? Is that good? Everybody, can you do the math? Great. So I get 1 half x squared minus 3 half x plus 2. X is between 0 and 4. Is that good or not? Yeah? Could you guys compute it just to be sure? So it's minus b over 2a, so it's 3 halves. Yeah. Okay. Now, where does this function achieve its minimum? This is a quadratic function, right? What do we know a quadratic function over R? So I have ax squared plus bx plus c, where a is non-zero. The vertex of this function is that did we see this? That the vertex of a parabola is that x equal minus b over 2a? Yeah? And that it's a maximum if a is negative and it's a minimum if a is positive, right? Did we see this? Yeah? We saw this? Okay, so this is a parabola where what is the value of a here? A is 1 half. So this parabola has a minimum on R. At what point is its absolute minimum on R? It's minus b over 2a. So it's 3 halves over 1. So 3 halves over 1 is 3 halves. Does it lie in this interval? Does it lie in 0, 4? It lies in 0, 4. Or if you forget about it, what can you do? You can differentiate it and solve for the critical numbers and compute the value of this critical number and at the endpoints. You agree? So f of 3 halves. Where are we? So it's f of 3 halves minus 1 half times 3 halves plus 2. What is that equal to? It's minus b. Okay, so do we remember what's the value of the vertex? I think it's minus delta over 4a or minus delta, can't remember. We just have to plug it in. Okay. Well, it's down here. Did we follow this or not? Everybody, did we follow what happened here? Did we follow this?
No.
Any questions on this? Please raise your hand. Yes.
Isn't it minus 3 halves over 1 half? Because it's minus b over a.
It's minus b over 2a.
2a.
The vertex is over minus b over 2a, and the sum of the two roots is minus b over a. Okay, I think so. To my memory. You know, so let's see, minus b plus root delta plus minus b delta. Okay, yeah. So the sum of the two roots is minus b over a. And the vertex is minus b over 2a. So it's 3 halves over 1. Okay? Have we seen this or not? Everybody, have we seen this before? No? We have not seen this. Okay, great. No problem. Take this function. Where it is? Take this function and find the maximum and the minimum on 0x4. So let g of x plus what? Plus 2. What is g prime of x? It's x minus 3 halves, right? Of course, the second derivative is positive, so you get a local min in that case. But this, in that case, is an absolute min. So what is g of 3 halves? So critical point number. And x equals 3 halves. What is g of 3 halves? G of 3 halves is, so it's 1 half times 3 halves squared, so it's 1 half times 9 quarters minus 3 halves times 3 halves. Well, that's good. Plus 2. So 1 half 9 fourths minus 9 fourths. This is just minus 1 half times 9 over 4 plus 2. 2 is 16 over 8, right? So this is 7 over 8. Now what is g of 0? G of 0 is 2. Let me put this here. G of 0 is 2. And what is g of 4? G of 4 is 1 half times 16, so it's 8. G of 4 is 8. 8 minus 6 is 2, right? 4, 2, 8 minus 6 is 2 plus 2 is equal to 4. So what is the absolute max? It's G4, right? Which is 4 here. Agree or not? And what is the absolute min? 7 over 8 on this line. So if x is equal to 3 halves, so f of 3 halves, what is the value of y if x is equal to 3 halves? It's minus 9 over 4 plus 2, right? Yeah? Minus 3 over 4 plus 2. So 3 over 4 plus 2, so it's minus 3 over 4 plus 8 over 4. 5 over 4. What is that equal to, did you say? It's equal to 7 over 8, right? And the maximum is that if x is equal to 4, so x is equal to 4, what is the value of y? It's minus 1 half times 4. it's minus 2 plus 2, which is 0. Oh, sorry, 4. So let's see, 4, 0. Wait, what? Yeah, okay. So I computed this line now. What else do I have to compute? Is it clear here? Folks, is it clear? Are we good here? Yeah, are we good? Following? Any questions on this one? Any questions? You're probably going to have to do this on your final, okay? It's going to be a long answer question. You may have to do something like that. Are we good here? Anything unclear, please let me know. Silent? Okay. Questions? Yes, sir.
You said we did after the OD of X minus
What? So I have this function. You agree? You agree or not? Great. You want to find the maximum and the minimum of this function. How do you find the maximum and the minimum of a differentiable function at closed vowel interval? You find the critical numbers, and then you find the value at the endpoints. And then you look at the smallest and the largest. That's what it is. Critical number, endpoints. Okay? Now, let's recall that I need an x and y coordinate, not only an x coordinate. So if x is equal to 4, what is the value of y? It is 0, right? And if x is equal to 0, what is the value? Well, sorry, if x is equal to 3 over half, what's the value of y? Say 3 over half here, 3 halves is here. Look at the value of 1. Minus 1 half times 3 over half, minus 3/4, plus, plus 2, which is 8/4, is 5/4. Agreed? All good? Now what do we have left? We have the third line. Third line is easy. How can I look at a third line? Oops. How can I look at the third line? What's the value of x? The value of x is 0, 3. X is 0. And what? And y is between 0 and 2, right? So what is F0y? What is that? It's x plus y minus xy. So it's y, right? You agree? Yeah? What's the maximum of x? What is the maximum here? Where is the maximum? Y equal to 2. Do I have F0, 2? No, I don't. So let me put it here. F0, 2 is equal to 4. And then where is the minimum? It's at 0. F0, 0 is equal to 0. Now, I have it already. So what is my absolute max? What is my absolute max? 4 is the absolute max. And what is the absolute min? 0. That's min. And how many points I reach for here? I reach 2, but it doesn't matter. I care about the absolute. Okay? Great. Now, so far so good. So far so good. I'll just make sure you practice a lot of this. I'll give you like a ton of homework so that you know you practice at home. And so this week, unfortunately, cannot have an exercise session. I'll just be focused on finishing your midterms. So I'll try to finish them by tomorrow. Fingers crossed, I'll be able to do that. So yeah, if they're all well, it should be easy, right? If they're good, it should be easy to go through them all. So I hope I could do that. Worst case scenario, Thursday. Thursday I will get it. Okay, great. We have an hour left. We'll try to finish another recorded topic called Lagrange multipliers and call it a day. Okay? Great. Will be a rough night for me as well today, so it's gonna second nuit blanche in a row. But that's fine. And the quiz 2 is up. Did you guys see it or not? Yeah, quiz 2 is up. It's a bit harder, I think, but it should be okay. Okay, it should be okay. Quiz 3 will be up today or tomorrow, and we'll do one quiz 4, and maybe a quiz 5. Okay? Yes. When is quiz 2 did I say? Friday? Friday. So I'll put the multiple choice today or tomorrow, so that you can. But work on it. Okay, quiz 2, work on it. Okay, it's important for the final as well. I can't remember what I really put on it, but it's. I think I chose like questions that are not very easy, but should be able to. Okay, great. So there is a last section of the course that should be on parametric curves. Now I will do this section, and it will be covered on the final. But the question is like free points. Like the question is, like you're playing soccer, the guy dribbles the keeper and he passes the ball. You just have to score. Okay. So the question is gonna be very easy. So so the material, this is what I want to say, I have it written. So the last class is on May 29th. May 29th is included on the exam. Okay, the exam is due 3. So you have how many days? 4 or 5 days? Very good. Now I'm on multipliers. Okay? I mean, the final, if I can say a word about it, it hasn't been reviewed yet, so it might change. But like the way it starts, the multiple choice, I think I had 15 of them, or 3 each, and 5 long answers. The way it starts is like, when you eat a wings challenge, like you start with like easy, and then you add the spice, okay, so I think the first 10, 11 multiple choice should be a piece of cake, okay, just like the web work, just like, I'm not saying they won't be tricky, but if you studied, you should be able to get them easily. From 11 to 15, they get slightly harder. I mean, that's fair, okay, they get slightly harder. Some of them are a bit hard, but, so like, yeah, it's not bad. It's not bad. Okay, great. Now let's do Lagrange multipliers. Now, suppose I ask you to find. Suppose I ask you, everybody. Yes, sir. The final 3 hours, yeah. It's on June 3rd. June 3rd from 9 to 12, right? Yeah.
Here or in the field house?
I don't know. They'll send it to you. I think it's in Trottier. That's what the email I got. So you'll have 3 rooms. But anyways. So now let's do the Lagrange multipliers. Now, what's the good thing about the Lagrange multipliers? There's an easy recipe to solve them. The bad thing is that the proof is a bit hard. And the intuition is kind of, they give an intuition, but
do you have to prove it?
You won't have to prove it. You just have to know the value. So there is an intuition for the Lagrange multipliers, but to be honest, for me it's not intuitive. So basically, they know there is, for me it's not intuitive. So I really cannot, the book has a nice explanation. For me, it's I don't really understand that. How they try to convince you, really. They try to convince you, say, oh yeah, that's it. Okay, they try to show you a picture. I mean, maybe we can draw a picture, but we can draw a picture and then try to convince you of the results. Good thing is that you just have to apply it, okay? Maybe we may be able to prove it later in the course. Yes, okay? So the Lagrange multipliers and constraint optimization. So in Calc 2, in Calc 1, you did these word problems, right? These optimization problems. So you wanted to maximize the area of a rectangle given that the perimeter is fixed. You remember this? So you had to maximize or find the maximum or the maximum say of xy, the area given that right? And then what do? You say, okay, let me transform this in one variable problem. Y is 25 minus x, right? So what do? You say x is, and you maximize this function, right? You remember this? We're going to do the same thing. Okay, we're going to do the same thing here, but now the thing is that you may not be able to solve for y easily. That's it. Okay, we're going to give a more general method where you may not be able to solve for y easily. Okay, now, okay, we agree. Like you did this in Calc 2, in Calc 1. You remember there's a big chapter at the end where you have things like that, word problems. So maximize the rectangle, the area of the largest rectangle, or that you can put in a circle, right? You remember these? Yeah. So it's going to be things like that. Now it's going to be only with numbers. I'm not going to do math. I'm not going to do a lot of word problems. Maybe in the web works I'll give you some word problems. But I'm just going to give you the results. Okay? Maybe a bit of motivation that I personally don't find very intuitive. At least. Well, anyway. Maybe you'll find it intuitive, but now suppose that I tell you really what you're doing here is motivation. You're finding the max or the value of fxy subject to gxy is equal to k, right? So you're finding the maximum of xy, so fxy is equal to xy, and the example below, and the example on my left hand, subject to is equal to k. So gxy is what? Is x plus y, and k is equal to 25. Right? So this is half the perimeter, right? Remember, so you want to find the rectangle of largest area whose perimeter is 50. 2x plus 2y is 50, right? And that's what you did. Yes? You remember this? Do you agree? Is this formulation clear? So I have to maximize xy subject to x plus y is equal to 25. Okay, so let's draw things. Let me draw the line x plus y is equal to 25. I mean, this is an easy example. This is why it's nice. And let me draw the line x plus y is equal to 25. This is the line x plus y 1. Okay? Now, of course, we're doing values of xy that are strictly positive, right? This is the line here. Now, I want to find the largest value of xy. What can you try? So let's try to put xy is equal to 1. How do I draw this in the plane? xy is equal to 1, this is y is equal to 1 over x. What is that? This is the one hyperbola, right? The 1 over x hyperbola. What is the answer then? 25 minus x. Where is the maximum here? The maximum is at x equal to 12.5, right? Max x equal 1 equals 25 over 2, right? Solve this derivative, or just say it's a parabola. The roots of the two parabola are 0 and 25. The vertex is the midpoint of the two roots, right? Do you know that? Yeah. And so x equal y equal 25 over 2. And what is xy equal to? This is xy, so it's 25 over 2, so it's 25 squared over 2 squared. Is that right? Is that right? Yeah. 25 over 2 squared, right? Yeah. Okay. Now really, well, just like that. Now, I want you to draw, or I want you to take this curve, xy equal to, well, I don't want a k, is equal to c. Okay? This may be a bit easier to motivate. What is the tangent line at a point? What is the slope of the tangent line? So you can solve y is equal to c over x. Do you agree? What is the slope of the tangent line? It's minus c over x squared. So y prime is minus c over x squared. Now, at what point let's do that. Well, can I write here? Yeah. At what point is the tangent line to y equals c over x equal to y is equal to y minus x minus 5? And what is the value of c? So really here, what you need is that you need to find a point x0, y0 such that minus c over x0 squared is minus 1, right? You want the slope to be minus 1. And what else do I want? And you want that minus x0 minus 5 is equal to c over x0. Yeah, I think that's it. So take c to be 25 over 4. Sorry, 25 squared over 4. And x0 to be 25 over 2. What is minus c over x0 squared? Minus c, it's minus 1. Okay, and what is the tangent line to this parabola? Sorry, 25 squared over 4. at the point where x0 is 25 over 2. How do you compute it? Y is just minus 1, right? The slope is minus 1, times x minus plus 0.5, right? Minus 25 over 2. Plus, what is the value of y at 25 over 2? So 25 squared over 4 divided by 25 over 2 is just 25 over 2. Is it 25 over 2? Yeah, so, no, wait. So it's minus 1, minus c over x0 squared, plus 25 over 2, plus 25 over 2, what do you get? You get 50 over 2. Yeah, right, so what do you get? You get 25. That should be 25. 25. So you get minus x plus 25. So if you let c equal 25 squared over 4 squared, and x to be 25 over 2, this line here will be tangent to the parabola. Okay, so if you draw your parabolas like that, let's do another way. If you let c vary, for example, well, I mean, those are not good because they should go like that. But anyway, the maximum will be achieved for the value of c such that the line y is equal to 25 minus x, it's tangent to the parabola xy equals c. This is the motivation for it. Is that something intuitive? It's not. For me, at least, it's not. Right? Okay. It's not a very intuitive thing for me. I mean, maybe graphically you can try to explain it, but this is the idea. Okay? What's the good thing? The good thing is that we don't have to know all of this, just have to know the method. Okay? Because here we're going to generalize this to another curve. Really what I need here is that the curve and xy equals c, for example, have the same tangent. And if they have the same tangent, what does it mean? Their gradients are parallel, right? If two curves have the same tangent line, then the normal vectors are parallel, right? So if I have two curves, they have the same tangent line, then the normal vectors are parallel. Okay? And this is going to be the idea of the thing. Now, there is a way you can prove it. This is a very important thing in convex optimization. If you're taking any class of convex analysis or optimization. But for now, we will just do the method. Okay. Suppose maximize, I'll do it in three variables, or minimize f, x, y, z, subject You can safely ignore this assumption.
I'll always make sure.
That this holds. Then, one can show that if fx0 is an extreme value, of fxyz subject to gx1z is equal to k, then the gradient of f is parallel to the gradient of g at that extreme point for some lambda. And how do we find this? I mean, this is so really how do we find this lambda? We have to solve a system. So what do the gradients mean? Gradients mean that fx x0 y0 okay, so how many unknowns do I have here? X, Y, Z, and lambda. How many equations do I need? 4, right? So the gradient will give me how many equations? 3, right? Fx, Fy, blah blah blah, is equal to lambda gy, and blah blah blah, and Fz, blah blah blah, is equal to lambda gz, the same blah blah blah, and then I have one equation, gxy. The 0 is equal to 0. And this will allow you to find, in general, the 4 unknowns, lambda, x, y, and z. Enough said. Let's do an example to see that this is really easy. It's not really easy, but it's easier than you think it is. Let's do an example. I don't want to do a useful example. I mean, we could do an example, the xy with the x plus y equal 25, and see that we get the same answer. Okay? Should we do that? Sure. Maximize. xy subject to x plus y equal 25 using Lagrange multipliers. Okay, so the Lagrange multipliers, because you have a lambda here. Okay, this is the Lagrange multiplier. Lambda is the. So what is my fx? fxy is what? Is xy. And my gxy is equal to what? To x plus y, right? Subject to gxy is equal to 25, and gxy is equal to x plus y. Okay, so what is the gradient of f? I need to solve 3 equations. What is the gradient of f with respect to x? What is fxxy? Is equal to lambda gxxy. And fyxy So what is fx(xy)? Everybody, fx(xy) is what? Differentiate xy with respect to x. What do you get? Y, right? So you have y. Gxxy, what is that? Differentiate x plus y with respect to x. What do you get? What do you get? X plus y with respect to x? 1. So lambda times 1. Now, fy with respect to xy with respect to y, what do you get? X. Gy with respect to g with respect to y, what do you get? 1. Lambda times 1, right? Now, you remember at the optimal value, what did we get? We get that x is equal to y, right? Do I have here that x is equal to y? X is equal to lambda, y is equal to lambda. And then what do you have? You have x plus y is equal to 25. How do you find everything? How do you find the values of x and y? Can you find them? So what is the x? So x plus y is equal to 25. So x is equal to y. So x is equal to y is equal to 25 over 2. And what is xy? Is that what we got before? Is that what we got before? Okay? Is it clear? Great, let's do one more. Let's do one more. This is, how much time do we have left? Do we have 30 minutes left?
5 minutes.
Not 5. No, we have 30 minutes, right? Okay, we have 30 minutes left. So we'll continue with 30 minutes. Let's do one more. Let's do a harder one. Great. So find the extremum of fxy so x squared plus y squared is equal to 1. This should be easy. That you can do it very easily actually. You don't need Lagrange multiplier for that. But let's not worry about it. Let's try with Lagrange multipliers. Do you see that? So if I take x squared plus 2y squared, I write it as x squared plus y squared plus y squared. I get 1 plus y squared. Okay? So you technically can do that. But let's try Lagrange multipliers. What is my fxy? What is my fxy here? Is x squared plus 2y squared. And my gxy is x squared plus y squared. Great, so what do I have to solve? fxxy is lambda gxxy. fyxy is lambda gyxy, and what as well? X squared plus y squared is equal to 1. I have to solve this system. What is fxxy? Can you differentiate fxxy? 2x. Can you differentiate gxxy? So lambda times 2x. And here what do you get? You get the 4y is lambda times 2y, right? And then you get x squared plus y squared is equal to 1. You can do it in many ways. So what do you get? You get x, cancel the 2. So you get x is equal to x lambda. Divide by 2. So you get y lambda is equal to 2y. And then you get x squared plus y squared is equal to 1. Great. What does the first equation tell you? What does the first equation tell you? Bring the x's together. What do you get? X is equal to 0, yeah. X is equal to 0, or lambda is equal to 1. Let's see. Y is equal to 0, or lambda is equal to, so I factor, let me factor out y, so what do I get? I get 2 minus lambda, right? And what does the third equation tell you? That x squared okay? We'll do a better one as well now. Afterwards we can do a word problem. Word problem. Find a word problem in the book. Okay. So, the first one tells you that x is equal to 0. Or lambda is equal to 1. Agree or not? So far so good? If x is equal to 0, what can you say about y? Y is equal to what? 4? Negative 1. You agree because of this equation? Yes or no? If x is 0, then y is equal to plus or minus 1. And what is the value of lambda? 2, right? You guys see this? If x is 0, then y is equal to plus or minus 1. Look at that here. What is the value of lambda? 2. So what do you have? You have the point 0, 1, and 0, minus 1. For lambda is equal to 2. Now, if lambda is equal to 1, what is the value of y? Y times 2 minus lambda is equal to 0. So y times 1 is equal to 0. Y is 0. And x is equal to plus or minus 1. Did you expect this or no? Did you expect that you get a point and it's negative or no? Did you expect that or not? X squared plus 2y squared. If you change the sign of x and change the sign of y, does it change the answer? No, so that's expected, right? So, what are my points? What are my points? I have f0, 1 and f0 minus 1. What are these equal to? X squared plus 2y squared is 2, right? And what do I have? I have f1, 0 is equal to 1. What is my absolute maximum? 2. What is my absolute minimum? 1. Easy, right? Slightly harder because you have that lambda coming in and you want to try to eliminate it. Okay? Yes, sir.
You already wrote the second line after the
Where?
0.
Here? Here? So, if really I just look at them here. Okay? So if lambda is equal to 2, what are x and y? So you have this, if x is equal to 0, y is equal to plus minus 1, and lambda is equal to 2. Right? So I mean, for the value lambda equal to 2, these are also the only points. Okay? Plug in lambda equal to 2, what do you get? 0 is equal to 0, that's good. X times 1 minus 2, so minus x is equal to 0. What is the value of x? 0. So if x is 0, what are the values of y? Plus or minus 1. Right? Because y squared is 1. So far so good? Yeah? Let's do one more. Let's see if the book has nice questions. The book will have nice questions. Okay, well, that's the next one. That's the next one. Well, let's do one in 3D. Or let's write let's if you want to write the recipe, you know, every method. So 2x plus 2y plus 2z. The absolute mass. And then of fx, y, z. X plus 2y plus z, subject to x squared plus y squared plus z squared is equal to 9. Is that what the book says? Let's see. Yeah. We do it? Yeah, we do it? Yes, sir.
Does the value of lambda mean anything? Like this would
Yeah, the value of lambda tells you how much the gradient is the scale of the other.
Okay.
Okay? So, yeah.
What does it mean when we say like it's subject to g and g is k?
So, subject to x plus y is equal to 25. Your g, x plus y is, your g x y is x plus y.
Yeah.
What do you want this value of x plus y to be?
You choose any constraint?
No, yeah, depends on the problem, right? What is the constraint? What is the g x y here? So what is my g x y is equal to 9, right? So let this be equal to g x y z.
Is there a relation between f and g? Then I could use something bigger than f as like constraining it, because that's what it means.
What do you mean bigger? What is
I don't get what like constraint means.
So if I tell you maximize the area of a rectangle such that the perimeter is 50.
Okay.
That's a constraint, right? You maximize xy such that 2x plus 2y is equal to 50.
Oh, so this is just another relation on x, y, z.
Exactly, it's another relation. Yeah. Okay, subject 2. Great. So what do I have to solve here? Who can help me with my 4 equations? Do you want me to write them all down? Should I write them all down or immediately? I write them all down? Do you want me to write fx is equal lambda gx, fy is equal to lambda gy, fz is equal lambda gz? Or I should just do it? Let me know. What should I do?
Can you do it right now? Again?
I write it? Yeah, sure. So what do I do? Fx is lambda what? Gx Fy and Fz and Gxyz Great, what is fx here? Who can help? Fx is equal to 2, right? Everybody, are we good? What is lambda gx? Gx is equal to what? 2x, right? What is fy? 2. Here, what do I put? Everybody? 2 lambda y. Okay? Then what is fz? 1 is equal to what? Yeah, say. Who was saying? Yeah. You said something? 2 lambda, that's very good. And what do I have? I have x squared plus y squared plus z squared is equal to 9. Great. Let's try to look at it from here this time. Let's try not to solve immediately. Okay, I will try not to solve immediately. Last time I solved immediately. Now let's try not to. Let's think about this. Can lambda be 0? So the idea, what's the idea here? You want to write that x is equal to 2 over 2 lambda. That's what you want to do. You want to do this, right? You want to solve for x. You want to write x is equal to 2 over 2 lambda. You agree or not? Can lambda be equal to 1? Can lambda be equal to 0? Why? So, if lambda is different than 0, then you can put 0 in the denominator. Okay? But first of all, we have to show that lambda is different than 0. What if lambda is equal to 0? What does the equality become? 2 equals 0. Does that make sense? No. We see that? We see that lambda is different than 0. So any solution to my system must have lambda different than 0. If lambda is 0, and before I don't think I could have done this earlier because I had x on both sides, right? If lambda is equal to 0, then I have 2 is equal to 2 times 0 times x, which is 0. Is this true? Can 2 be equal to 0? Can 2 be equal to 0? No. So lambda is different than 0. Great. What is x in terms of lambda? X is 2 over 2 lambda. We agree or not? What is that? This is 1 over lambda. What is y? Y is also by the second equality is equal to what? 2 over 2 lambda, which is 1 over lambda. And what is z equal to? Is 1 over 2 lambda. Okay? It's better to keep the 2 over 2 lambda. Great. So I have x, y, and z in terms of lambda. How can there is one more equation that I didn't use. What is this equation? X squared plus y squared plus z squared is equal to 9. Now, do I plug in the x's or the lambdas here? The lambdas. So I have what is my unknown here? I have one equation and one unknown, a quadratic equation. So what is it? So it's 4 x squared plus y squared plus z squared is equal to 9. So 1 over lambda, so it's 1 over 4 lambda squared. Z squared is 1 over 4 lambda squared. Here, what do you get? You get 4 over 4 lambda squared, right? Plus, what is z? Is 1 over 4 lambda squared, right? Is equal to 9. Great. Let me multiply both sides by 4 lambda squared. What do I get? I get 8 plus 1, which is 9. 9 is equal to 9 times 4 lambda squared. So what is 4 lambda squared? Everybody? 4 lambda squared is equal to 1. So what can I say about lambda? It's plus or minus. Lambda is plus or minus what? 1/2, right? Now, if lambda is equal to 1/2, what is my value of x? If lambda is 1/2, x, y, z, what is that equal to? 2, and 1, right? What is x of 2, 2, 1? It's 9, right? 4 plus 4, that's good, very good. Then we have x. What is the absolute max? What is the absolute max? 9. What is the absolute min? Okay. Great. So I will not. That's good. I think it's. Somebody changed their place here. I just can't figure out. Did anyone change their place here? You changed their place. Okay. Okay. Because like the setup is not the same. And then. Okay. I just realized like some changed their place. Okay. I thought like. Anyways.